Next, we will see the application of Ampere's circuital law. We'll be seeing it for two important devices, out of which one is known as solenoid and the second is known as toroid, T-O-R-O-I-D. Okay, those two are the important applications of this, right? Now, if you see, what are we interested in this topic? Application of Ampere's circuital law for solenoid. So when I take a solenoid, basically what is a solenoid? Observe. So if I take this to be a core is something which is holding the wire. So around this core, I'm going to wind the wire like this. Like what am I doing? I'm just winding the wire like this. Then this wire is what is called, this kind of an arrangement is what is called as a solenoid. So solenoid is basically a helical winding of the wire around a core, right? So when you observe this on the paper, right? So how will it be is, see, suppose now, if you observe it on a paper, let's say that the current in this conductor is flowing from the bottom to the top. So at the top, how is it entering? Is it entering into the plane or is it out of the plane? So it is entering into the plane, and at the bottom, it will be out of the plane. These are the 2 points that you need to keep in your mind. So when you see from this side, how does it look like? It looks like a circle. Whereas when you look from this side, it will look like some other shape. I'll draw that shape and show you. So basically, this is the cross-sectional area of a cylinder, right? When you see from this side, you're able to see the circular part. Whereas when you see from this side, are you able to see the complete cylinder? You're only able to see the front part of it. No, when the front part is projected on the paper, it has a different perspective. Okay, observe how it is going to look like. Right. Now, if you see, basically, how is a solenoid going to look like? Let's say there is a core onto which there is a wire that is wound like this. So in the example that I considered, I'm saying that the current is in this direction. The way I showed you, the current is in this direction, so that at the top, the direction of current is into the plane, and at the bottom, the direction of current is out of the plane. Clear with this? Right. Now, what we need to do here is, we need to consider the Ampere circuital law and solve this problem. Right? So that's what the problem statement is. We need to find what is the magnetic field generated due to this kind of a circuit called as the solenoid, right? For that, observe, this is cylindrical, right? When you take a cylinder and project it on a two-dimensional plane, on a two-dimensional surface, a cylinder will look like a rectangle. So cylinder projected, a three-dimensional shape projected on a two-dimensional surface is going to be a rectangle. Okay. So when you take this rectangle, right, when you take this rectangle, at the top, the current is going to be into the plane, and at the bottom, the current is going to be out of the plane. So here, into and dot represents what? They represent the direction of current. So don't get confused thinking that it represents the direction of magnetic field. No. Am I clear with this? Right. Now let me take the length of the solenoid to be L. So what did I do? I took the length of the solenoid to be L, and I took the number of turns in the solenoid to be capital N. Right. So can I define a parameter called as capital N divided by L? So what is this basically? It is the number of turns per unit length. So number of turns per unit length. This is represented as small n. So remember, in physics, always remember, in physics, capital N is used for number of turns, small n is used for number density. So here, what is the number density it is representing? It is the number of turns per unit length. Am I clear with this? Right. Now, if you see, What is that we need to do? We need to apply the Ampere's Circuirtal law. So for Ampere's Circuirtal law to be applied, I need to consider an Amperian loop symmetric with respect to the current distribution. Symmetric with respect to current distribution. So if I look at this rectangular shape, what I will do is I'll consider an Amperian loop in such a way that it is going to be a rectangle, because for rectangle, then other symmetric shape I can think of is another rectangle only. No? I'll consider the rectangle in such a way that the half portion is inside the solenoid and half portion is outside the solenoid. Right? So half portion is going to be out of the solenoid. Now, if I take this length to be, okay, suppose I take this length to be small l, right? And I take the number of turns to be n dash, okay, or else I'll do one thing. I'll take the number of turns to be n dash and the length of this portion to be l dash. Okay, so that here one thing that is there, n dash divided by l dash. What does this represent? This is also going to be number of turns in this length, number of turns per unit length, where this value you should not write it as small n dash, rather it is small n only. Means number of turns can change, length can change, but the ratio of those two quantities will always be a constant. That is how the windings are. The windings are equally spaced. How they play? The windings are equally spaced. Am I clear with this? So number density is going to be the same, right? So what do we need to do? We need to calculate the magnetic field due to this shape. So how to proceed? So I've considered the Amperian loop also. We have considered the Amperian loop. Let me say this is A, B, C, D. Okay, the loop's name is A, B, C, D. Now listen to this carefully. If the current is into the plane, what is going to be the direction of magnetic field? So if I take my thumb and place it in the direction of current at the top, so when I place it in the direction of current at the top, when I curl my fingers, the magnetic field is, look at my fingers. The magnetic field is in this direction. So magnetic field is going to be in this direction, right? Now, if you observe, out of the surfaces AB, BC, CD, and DA, what is going to be the angle between the magnetic field and AD? What is the magnetic field between B and AD? It is 90. So AD will not participate in the Ampere Circuirtal law. So what is the angle between B vector and AB? 0. So that will participate. What is the angle between B vector and BC? Again, BC and B vector. BC and B vector. They both are perpendicular to each other. Now, what about B vector and CD? 0. But one point that you need to consider here is when I say the solenoid here, right? In your physics, the solenoid that we consider is a long solenoid. When I say long solenoid, the length of that solenoid is going to be very large compared to its thickness. Right? So length is going to be large compared to its thickness. So that's what is meant by a long solenoid. So by default in physics, whenever they say solenoid, they're referring only to a long solenoid. So for a long solenoid, what will happen is the magnetic field outside the solenoid will be 0. So magnetic field outside the solenoid will be 0. So the magnetic field for a long solenoid will exist only within the solenoid itself. So which is the only portion of the Amperian loop which is going to participate in the, it is AB. So what I will do is line integral of B vector dot dl vector is equal to mu naught into the charge enclosed by whom? By the Amperian loop. Right. So here B vector and L vector are in the same direction. So what is the length of AB? Let's see. So here I will write it as AB. I hope you're able to understand this. Okay, to be more specific, I'll write it as BA, because I told you, DL vector generally will consider it in the direction of magnetic field itself. I'll write it as BA. So what will be the angle between them? 0. So what will get multiplied? Only the magnitudes. So the line integral of dA, which is going to be b into dl, will be equal to mu naught into. So what I need to calculate is the current enclosed. Listen to this carefully. Okay, listen to this carefully. So what is going to be the value of current that is enclosed in this surface? What will be the current that will get enclosed in this region? So tell me, in this region between A to B, how many windings are there? The region between A to B, how many windings are there? N dash windings are there, right? So each winding carries a current of I. How much is each winding carrying? I. So N dash winding will carry a current of N dash I. Got it? So the total current that is enclosed here is going to be N dash times I. Make sense? Am I clear till this point? So N dash into I. So B can be taken out of the integral. B into the line integral of dl from B to A is going to be how much? I'll first finish this. B into, what is the line integral of dl? So what is the length of AB? Length of AB is L dash. So capital B into L dash is equal to, what is there on the right hand side? It is going to be mu naught into N dash into I. So what will be the value of B? It will be mu naught into N dash divided by L dash into I. What is N dash by L dash? Small n. So this will be equal to mu naught times N into I. So the magnetic field due to a long solenoid is going to be mu naught into N into I, and this value is going to be the magnetic field which is present at the center of the solenoid. Right? This value is to be remembered. It is a very, very important one. We'll use it in the next chapter also. So what is going to be the value? It will be mu naught into small n into I.